Lab for Oscillations. So the purpose of this lab was to observe and analyze the motion of a mass in the spring, and with this create a computational model to predict motion. And then we were to compare the observed motion with that was predicted. And my results were that my model is accurate in depicting my observations. So some concepts used, we're using Newton's second law again, in which F is equal to ma. With some alterations to these equations, we get two equations that one predicts the final velocity of an object and one predicts the final position of the object. These are extremely pivotal in our Python code for later. A second model used, which is different from the previous labs, is the energy principle. And then for this lab, we know that the changes energy is equal to the work plus the heat transfer. In this lab, we have no heat transfer. And for this lab, we're setting our system equal to the spring, the mass, and the earth. Therefore, there are no outside forces acting on it, and and the work is equal to 0. Therefore, delta E is equal to 0. So for our delta E, it's composed of kinetic energy and potential energy. So our change in kinetic energy is here, our change in potential energy of the spring is here, and the change in potential energy of the earth is here. And these will be discussed in more detail later. So our observations through tracker. So first we set our coordinate system with the origin at the fixed point that our spring hung by. We then calibrated its length to 0.702 meters, and we calculated its point of mass at different instances along its route. It's also important to note the initialization from tracker. So we have the spring's mass is 0.402 kilograms, its initial position as negative 0.119 meters in the x direction and negative 0.683 in the meters in the y direction, and it has 0 initial velocity, and the length of the spring again is 0.702 meters. We also need the table that we got in tracker of its position versus time to create a CSV file. And then the CSV file will be extremely pivotal in our Python code later to predict, to compare our predictions of energy with what we had here. Now that we've run our video through tracker, we can now make our Python code. So as a G, the gravitational constant 9.8, and a J hat, which is our spring constant is 6.86, which is found by looking at the period of oscillation. From our spring constant, we can find the relaxed length of our spring. So with this, we can then find the vector L as well as L hat and S. So another thing I'd alter was the gravitational force, which is just negative mg, and we need the j hat vector to make this into vector form. We have the force of the spring, and that both of them added together is our F net. Our ball velocity is found through Newton's second law. The new position update is then found by now we need to update the spring again, which we did previously. And with this, we can see what we get. So here we see our oscillation of the spring. Here, this graph shows the x-coordinate, and this one shows the y. And we can see here that the y is less dynamic than the x, but we can see when we were looking at the simulation that the ball did move more in the x-coordinate. Now we can focus making a Python code focusing on the energy principle. Our delta K is equal to 1/2 mv final squared minus 1/2 mv initial squared. Our potential energy of the spring is equal to 1/2 the spring constant minus times the magnitude of the spring's new length minus its initial length squared, and the potential energy of Earth is equal to mg8. So into our while loop, we set that the K initial is equal to the K that we just solved for, and the UG initial is equal to the UG we solved for, as well as the US initial. These are going to be changing, so that's why we have to state another value to it. So next thing we have to do is update the new K's, the new UG's, and the new US's. So after we run this, we get this nice graph. We have that The blue is representing the change in kinetic energy. The red is representing the change in the spring's potential. The green is representing the change in gravity's potential energy. And we have the yellow is equal to the delta K plus the delta U plus the delta UG. As I stated earlier, these should be summed up to 0 because there is no work acting on the system. Now we compare this energy data with the data that we got from Tracker. So now first what we need to do is upload our CSV file that we created earlier with our information from Tracker right here. Now we have to go alter its while loop that corresponds with the information from Tracker. So when we run our module, and when we just look at the picture of the spring moving, we see that the two balls are very close to each other. However, we do not necessarily get a good idea of how close they are. So when we look at the graph of the two together, we are able to see that the two graphs overlap, and that now we can conclude that the model that we created very much accounts for the observations.